Let's imagine, so let's review circular motion. Remember that whenever you're going to go in a circle, you need to associate going in the circle with the property of the acceleration, which was, remember, every time you go in a circle, the direction of the acceleration is radial and directed towards the center, not outward. This is a fake acceleration, doesn't exist. It only shows up if you change your coordinate system from Cartesian to polar. You'll see this in C271. So when you go in a circle or you're doing circular motion, the acceleration that causes you to go in a circle is what we call the radial acceleration, which is towards the center of the circle. And its magnitude is related to the tangential velocity, such as A is equal to V squared over R. If you decide to go, and it's going to be for uniform circular motion, if you are considering a non-uniform circular motion, you may be able to accelerate faster and faster as you go in a circle. If you want to do this, you need another component of the acceleration, which is called the tangential acceleration, the one that's parallel to the velocity. That one will change the magnitude, while the radial, which is always perpendicular to the velocity, which in turn is tangential, will cause the change of direction. But in both cases, at each instant, you can deduce and relate the acceleration magnitude with the velocity magnitude with A is equal to V squared over R. All right, so until we get to chapter 10, we will only consider the radial acceleration. So we're going to use the exact same technique as before. Whenever you pick a coordinate system, pick one of your axes along the direction of the acceleration, which means that all you have to do for circular motion is identify the circle around which you're going around. And that's it. And then pick, say, you positive x in that direction, bing, bang, boom, done. If you don't do this, you're going to have to convert and express your acceleration vector in both x and y component, x and y axis. And usually people who go in that route never get it right. So use the same technique, identify the circle around which you're going under or around. Therefore, you know where the direction of the acceleration is. Pick one of the two axes in that direction. For example, if you are on ice and you're driving a car, you're driving into the board and you're sliding on ice, can you turn? Well, I don't know. If you're from here, you may not have experienced this, but if you're from a snowy country, or maybe even if you're not, Tyson suggests, no, you can't turn. He's right. Can turn left, can turn right, Zoolander 1, Zoolander 2, don't matter. You're toast. You gotta go straight. Okay? For you to be able to turn, you need to have a change of velocity in the horizontal direction, which means you need to have an acceleration in the horizontal direction, which means you need to have a force. So if you go straight into the board, there is no way you can turn. The only way you can turn is if you have friction, because then you're going to turn your wheel, and the friction as the wheel are going to rotate, and your wheel is being lifted, tilted in this direction, and is going to rotate that way, then friction is going to go opposite. Hey, go away. And it's going to push you in that direction. So it's actually static friction that will allow you to turn. We're going to see this in detail, very much detail in chapter 10, as we were rotating our tire instead of sliding. But if we both agree that if you have no friction and you're trying to turn as you go straight into the board, you can't. You have to have a force on the horizontal direction. But if you cannot create that force from your engine, or if you have no friction to help, the only way to be able to turn is to lift the ground. If you lift the ground that way, then you can turn left. If you lift the ground that way, then you can turn right. So because this, remember, will not create a force, but it will change the direction of the weight. Now the weight has a component that way, or a component that way. This is the component of the weight that will allow you to take a right turn, and this is the component of the weight that will allow you to take a left turn. So just by lifting our plane to an inclined plane, again our favorite inclined plane, we're changing the orientation of the weight with respect to the plane. So we don't need to invent a new force that will allow us to go left or right. We're just going to use the new component created by the inclined plane of the weight, and this is the component that will allow you to take a left or a right. So as you have turned with your car, let's say on the Pali or the Like, and you have those turns going wow, wow. If you're going down into the plane and you're taking a left because the road is like this, if you go super, super fast, what is your tendency of motion in addition to into the plane? If you're trying to increase your speed, increase your speed as you're taking a left on that road, which is inclined, well, what do you feel? What is the car tendency to do? Yeah. Tendency is to go up. So if there is no friction in there, you will go up if you go too fast. If you don't want to go up, you need to slow down. Then you can stay on track. If you don't go fast enough, you will slide down. So you need to find the correct relationship between the velocity and the angle for you to stay on track or on the track. If you're going on a car racing little thing. If you have friction, no problem. It can help you, which means that you can go faster. Because if your tendency is to go up because of the high velocity, then friction is going to be created and go opposite. This is static friction, not kinetic friction, because you have tires and wheels. You don't skid, you don't slide, you roll. No puns intended, and no drugs involved. So it is important to realize that this is going to be the friction and the static friction that is involved to keep you on the track. If you're going too fast, static friction will go down to keep you there. If you're going too slow, it will change its direction up, and it will keep you from sliding down the inclined plane. Okay, so we're going to do both situations, with and without friction. The friction on the tire should be upright. If your tendency is to go down, that is, you don't go fast enough. If you're going super, super fast, then your tendency of your car is to slide up the ramp. Hence, the direction of the static friction will flip, and it will be down the ramp to keep you on track. Does that make sense? Perfect. We're going to revisit all this in detail in chapter 10. So if this doesn't make 100% sense, it is because we're considering a rolling system and not a setting system. We have wheels, and we're only going to look into rotation in detail in chapter 10. So we may not have all the tools to really fully appreciate and understand this. So if that's the case for you, check out your book and look at bend curve. They may have new complementary information, or just take it and memorize it for now, and then you will appreciate it in chapter 10. That is, if you go into the plane and you try to take a left, having lift the road like this, if you go too fast, V is big, your tendency is to slip up. If your tendency is to go up, by definition of friction, got to go down. Hey, what happened to, oops, I lost my down. But if your velocity is very small and you want to take a left, your tendency of the car is to slip down, therefore friction will be up. The car is moving into the board, perpendicular to the board. All the cases we discussed, the car was going into the board. Okay? So, if we don't consider friction and we want to take a left, I need to incline my plane by an angle alpha, and this is my car. If you look at the motion of my car at this instant, you can always identify a circle whose center is around here at the same level. So again, remember the car is going into the plane. If you lift your road with this angle theta, this car at this instant can be modeled as going around an imaginary circle whose center is right here into the plane. So I draw it like this, but it should be, perpendicular to the plane. Okay, that's the key to bank curve. Mistake is to assume that the circle is along the inclined plane. No good. The instantaneous circle is not parallel to the inclined plane, it's parallel to the ground from which the road is being inclined from. Okay? Which means that the acceleration is in this direction. How come I cannot change my color anymore? Here. Okay? That's the key to bank curve. Because once you have identified the direction of the acceleration, then you know which coordinate system to pick. If you want to take a right, at this instant, you are rotating about an imaginary circle whose center is here, like this. Not like that. So the red is the no good. The purple is the correct one. Okay? So this would be the radius, the instantaneous imaginary radius of the circle around which the car is rotating about at that particular instant. That's the key to bank curve. So that's something you should make a good note of it and keep it right next to you every time you're going to have a bank curve problem. Because now we can identify by how much we need to lift that inclined plane for us to stay on track. Oh, John King, with a higher velocity, his tendency is to really slide up, right? His tendency is to go straight, which just happens to be up. Well, we're going into the plane, right? So the car is going into the plane. So the velocity is straight. But in addition to this, as you leave the road, if you're going too fast, you're going to have another tendency to go up the inclined plane. Nobody was like 16 or 18 or when you had your first car and you're going like, and you take a like big turn or short turn and you're going super fast. You never skid on the opposite direction? You never did this when you were young? Thank you, Tyson. I'm going to get in trouble. Don't try it at home. But I mean, you've seen, I don't know, what is the car movies? Fast and Furious number 47. You have like 46 movies where you can watch this. When your car, drifting. Thank you, Tim. That's the keyword that I was looking for. Drift. So if you try to take a left and you're going too fast, you're going to drift up the ramp, right? And if you're trying to take a right and you go too fast, you're going to drift on the opposite direction. That's what I'm after. So if you actually drift, if you don't want to drift, then you need the help of static friction, whose direction is opposite to the tendency of drifting. Does that make sense now that we have that keyword? Thank you, Tim. John, Ray, everybody else? Perfect, true. So watch whatever that stupid movie is, Furious, whatever, the Bullhead guy. So let's, whoop, go away. Okay, let's consider a case where we have no friction. And let's identify the maximum angle for specific velocity so that there is no drifting. That is, if you're trying to build a road and the county and city and county tells you on that road the velocity must be whatever, 35 mph, kind of go faster. You need to build that road so that as you lift that road to allow people to take a left, they can do it safely without drifting. Let's consider a case where we are on ice, and then let's add friction for a more realistic case. I want to take a left. So again, I have identified the fact that I'm going into an instantaneous circle, which is horizontal, of radius r. So I'm giving r, I'm giving v, I'm looking for alpha for a particular mass of the car. Let's do a free body diagram. We're going to have the weight. We're going to have the normal force. And that's it. And remember, the velocity is perpendicular to the board. But that's pretty much the only two forces we have, right? Weight, normal, nobody's pushing us or pulling us, and we don't consider friction for now. We're going to add it after. So that's it. Very simple problem. But again, we have identified the fact that the acceleration is horizontal, and we know, because we can consider this as an instantaneous circular motion, we know that A is equal to v squared over r. So let's see that later on. So we're given v, and we want to figure out the maximum alpha that we can use. Let's do a free body diagram. Let's pick one of our axes x along the acceleration, which means that alpha now is between n and y. Since we picked x in the positive direction of the acceleration, this is ma, and this is 0. And since we know it's a circular motion, this is m v squared of r. So far, so good. Now let's look at the forces in the x direction. Well, that's trivial. You only have one. It's n sine, and that's it. And in the y, where there's no acceleration, we're going to have n cosine minus mg. That's it. Let's get rid of the normal force because we don't care. So we can solve for normal force in the second equation. We have mg divided by cosine. Let's substitute here in the first. And now we have m v squared over r is equal to the normal force, which is mg divided by cosine alpha times sine alpha. Hence, sine alpha. Behave. Pen. And now we can solve for and relate alpha with v. Tangent gr alpha. If you are given the velocity from the city and county and want to build that road, then you solve for alpha. That would be v squared over rg, and you're going to take the arctangent of this. This will allow you to build that road so that if you consider an icy road for that particular velocity and that particular radius of curvature r, which depends on the way you build it, and alpha, which is the elevation you're going to pick, then that car ain't going to slide. It's going to stay on track. A beauty. Now, obviously, that's not a very realistic case. We always have friction. Let's redo the same problem, but this time let's look at what is Vmax if we have friction. Obviously, if we have friction, we can go faster. Free body diagram. Still the weight, still the normal force, and now we want to go and trying to look for the maximum velocity, which means that our tendency of drifting is up the ramp, and friction is down. And it's static friction because we're drifting, skidding up. Since we see the keyword max, then the static friction also takes maximum value. You want it to take its maximum value to help us as much as possible. So this is mu s n. That's it. So just one more force. Obviously, you know and you can guess that this force is in the same direction as your acceleration, so it's going to help it. No problem. Same as before, the acceleration is in this direction, therefore pick your x in the same direction. Alpha is still here, and now alpha is also here. So you just have one extra force. Ooh, no biggie. Let's project both. Again, the top one is ma, which is mv squared over r. And the second one is 0. So same as before, n sine alpha, n cosine alpha, minus mg, but now we have the friction. This is a positive friction, negative mu s n cosine, and this is negative mu s n sine. That's it. So just two more terms, one in each. Now we can solve for v. Same thing, we're going to get rid of the n force. Let's do it. N is going to be equal to, what do we have? We have mg divided by cosine alpha minus mu s sine alpha. All right, let's substitute in the first equation. Mg, we can factor the n out. Cosine alpha minus mu s sine alpha times sine alpha plus mu s cosine alpha. And this is equal to mv squared over r. And this is our Vmax. So now we can solve for Vmax. The mass is irrelevant in all cases. Vmax is gr sine alpha plus mu s cosine alpha divided by cosine alpha negative mu s sine alpha. So given this particular construction with this particular r and alpha, this is the maximum velocity if you consider friction. And of course, you can go the other way around and solve for alpha in terms of v. Now, if you're looking, the beauty of this is if you're looking for v min, what will be different? The tendency of the car is to drift down the inclined plane. Hence, the only difference is you flip the frictional force, which means you flip this sign, you flip this sign, which means you flip that sign, and you flip this sign. Hence, pooch, pooch. And that will be Vmin. And it makes sense. If you have a positive sign on top and a negative sign on the bottom, the numerator is big because you add, and you divide by something where you subtract. So the denominator is going to be small. So a big number divided by a small number is going to give you Vmax. While Vmin, you have a negative number on the top, so you have a smaller number, and you have a positive number in the bottom, so you have a big number. So now a small number divided by a big number is a smaller number. That's Vmin. So that's consistent. Okay? So now you can solve for Vmin, Vmax, with friction, without friction. So all you have to care now is go back to the engineer and ask them, the ME people, as you build your road, okay, I'm going to build it with this particular angle, alpha, with this particular radius of curvature, r. Now, what is this static friction between tires and asphalt? And then they will give you a range. You're going to take the safest one. So either the lower limit or the higher limit, depending on what you want to do. And then you're going to be able to tell the city and county, okay, on that road, on that turn, the maximum velocity must be this. So as engineers, you can even tell them, this is the restriction. We have to build a road that way. You have to change the maximum velocity to be safe.